In Related Rates, Pencast, Parts 1, 2, and 3, we've solved 3 different variations of a related rates problem regarding a rectangle. Let's solve one last variation. I'm hoping you now understand the 4-step process for solving related rates problems and can apply that. The length of a rectangle decreases at a rate of 5 centimeters per second. The area increases at a rate of 2 square centimeters per second. Find the rate at which the width is changing when the width is 8 centimeters and the area is 12 square centimeters. So the first step is to, as we've indicated before in our 4-step process, is to identify the rates in the problem and to write them as derivatives. So this 5 centimeters per second is the rate at which the length is decreasing. So the length is decreasing at a rate of 5 centimeters per second. So the rate of change of the length with respect to time is negative since the length is decreasing. Another rate, 2 square centimeters per second. That's the rate at which the area is changing with respect to time. But that's positive 2 square centimeters per second since the area increases. And I want to find the rate at which the width is changing, dw dt. Now let's use our common sense here for just a minute. If the length is decreasing and the area is increasing, is the width going to be increasing or decreasing? Think about that. Make up your mind and then think about at the end if what we get makes sense. What do you think? The length decreases, the area increases. The width's going to have to increase, right? Let's see if we get, in the end, dw dt is a positive. That would be a good check. If we get dw dt is negative at the end, that would indicate we've made a mistake, wouldn't it? Okay, step 2 of our 4-step process. Look at the notation for the derivatives we've written. The dependent variables are L, A, and W. So we need an equation that relates L, A, and W. Well, the shape's a rectangle, and I know that area of a rectangle is length times the width. Step 3, take the derivative of both sides of this equation that you got from step 2 with respect to time. Now, I've often seen students think that they have to solve A equal L times W for W, since I'm trying to find the derivative of W with respect to T. Well, if you want to solve this equation for W, that's fine. You're going to get W equals A divided by L, but then when you differentiate, you've got to use quotient rule. And that's fine if you want to do that, but solving for W really isn't necessary. I'm going to take an implicit differentiation mindset and just differentiate both sides of my equation with respect to time. In fact, that's what I always do in a related rates problem. It just saves some messy algebra. Okay, my L and my W are changing over time. Neither is constant, so I'm going to need to use the product rule. I can't just assume L and W is constant. So product rule first times the derivative of the second plus the second times the derivative of the first. So now notice that I have an equation that relates all the derivatives in the problem. Step 4, I substitute the values that are in the problem in for the quantities in this equation. So I just take this equation and substitute what I know. dA dt, derivative of area with respect to time, is 2 square centimeters per second. So I'm replacing dA dt here with 2 square centimeters per second equals L. Well, I don't have L, do I? Oh, but I've got width and I've got area, so I can find L. Because I've got width is 8 and area is what? 12. And I know that L times W is A. So L times 8 centimeters is what? 12 square centimeters. So the length is just 12 square centimeters over 8 centimeters. So the length is 3/2, isn't it? Centimeters. 1.5 centimeters. So at this instant in time, at which I am wanting to compute dW dt, the rectangle has a width of 8 centimeters, an area of 12 square centimeters, and a length of 1/2 centimeter. So at this instant in time, L is 3/2 centimeters. I want to find dW dt. W, I know is what? 8 centimeters. I'm just substituting into this equation. And dL dt is -5 centimeters per second. So I've got 2 centimeters squared per second equal 3/2 centimeters times dW dt minus 40 square centimeters per second. So I'm solving this equation for the symbol dW dt. I'm through with the calculus. No more calculus in this problem. This is all algebra. This is like Algebra 1 solving a linear equation. I'm solving for the variable dW dt. That's how I need to approach this algebra. So I want to add the 40 square centimeters per second to each side, because I'm trying to isolate what I'm viewing as a variable I'm solving for, dW dt on one side. So I get 42 square centimeters per second equals 3/2 centimeters times derivative of W with respect to t. So now divide both sides by 3/2. And that's the rate of change of the width with respect to time. Notice this is positive, right? And didn't we say that the answer had to be positive at the beginning? Because if your length is decreasing for a rectangle and your area is increasing, well, the width has to be increasing, right? So I would expect dW dt to be positive. And sure enough, it is. Specifically, what positive number is the rate of increase of the width with respect to time? Well, it's 42 square centimeters per second times 2/3. And when you divide square centimeters per second by centimeters, I'm going to get centimeters per second. When you divide by 3/2, you multiply by 2/3. So I get 84 over 3 centimeters per second.